In this video, we're going to put together all of the various theorems and definitions we've looked at here in this section and develop a method for finding absolute extrema. We're going to require a little bit more work in order to find the relative extrema, and we'll discuss that in section 4.3. But until then, focusing on absolute extrema, we'll do the following. First, we're going to assume that f is continuous on the closed interval a to b. Then we can apply both the extreme value theorem and Fermat's theorem to locate our extreme values. Here are the steps. We'll start by first finding the critical points of f in the interior. Remember, your critical points are the points where f prime of c equals 0 or f prime of c does not exist. So what this means is that we will need to use the differentiation techniques that we developed in chapter 3 and determine where that derivative equals 0 or is undefined. This is going to require a little bit of equation solving. Next, we will evaluate our original function, f, at each of the critical points, and also at the two endpoints. So once we've located those critical points, we'll plug those points back into the original function and also plug the endpoints in. Because in step 3, we're going to look at those values and find which is the biggest and which is the smallest. The biggest will be our absolute maximum value, and the smallest will be our absolute minimum value. So one more time, just to recap. Given a function on a closed and bounded interval, we will start by differentiating that function and then solving for where that derivative equals 0 and where that derivative is undefined. This will be the hard part of these problems. Once we've located all of those critical values, assuming that they exist, we will evaluate our function at those points, and we'll also evaluate it at the two endpoints. We'll compare our results. The biggest is our absolute maximum value. The smallest, our absolute minimum value. So let's see an example. We'll start off with a nice polynomial function on the closed and bounded interval -2 to 3. Our first step is differentiating. So here we will apply our power rule, and we get the derivative 12x cubed minus 12x squared minus 24x. Our next step then is to find the critical points, which means determining where this derivative equals 0. Now, in general, we also need to consider where the derivative is undefined, but since our derivative here is a polynomial function, and we know that polynomials are defined everywhere, we don't have to worry about this derivative being undefined. We'll see some examples of this later on in this section. Well, in order to help us solve this equation, it'll be helpful to begin factoring our derivative. So we'll start by noticing that we can factor a 12x out of our polynomial. And we can then factor x squared minus x minus 2 into x minus 2 and x plus 1. This gives us a simple polynomial equation to solve. If we set this equal to 0, then by the zero factor property, we just set all of our factors equal to 0. And we get critical points of x equals 0, x equals 2, and x equals -1. Now, at this point, it's good to go back and take a look at the original interval that we were considering. If any of the critical points that you found are outside of this interval, toss them out, ignore them, cross them out. We don't care about them. We're only looking at what is happening on the given interval. Unfortunately for us, all 3 of these points are located in this interval, so we will need to check all 3 of these points. So now that we have located our critical points, we will plug all 3 of these points along with the 2 endpoints back into the original function f of x. So evaluating all 3 of these critical points along with the 2 endpoints of -2 and 3, we get the following values: 32, -5, 0, -32, and 27. All that remains is to go through and pick the biggest and pick the smallest. Well, 32 is the biggest output. -32 is the smallest. So this would be our absolute max, and this would be our absolute min. On the left, we have a graph to confirm our results, and we can see that, sure enough, the left endpoint is the largest point on the graph, and the critical point of 2 produces the smallest point on our graph. And we've determined where the absolute max and absolute min occur. This is the same process that we will use throughout the rest of this section. Find the derivative, locate the critical points, evaluate the original function at the critical points and the endpoints, find the biggest value, find the smallest value. We'll see more examples in future videos.